Okay, here we go in our next section. We're going to call this 6.10, which is trigonometric substitutions. This continues on from us learning how to integrate with using U substitutions to undo chain rule. Integration by parts is undoing product rule, and so we were getting into some kind of heavy ideas in here. This next one's trig substitutions. Looks at a number of different parts, uses some trig identities from Math 30-1 that we had learned back then, uses some of the strategies that we were looking at with doing U substitutions. And so we're going to get into this. We're going to break it into a few different scenarios of what this looks like. This first one is called type 1. And so let's get at it. Substitution by U for type 1. If type 1 looks like this, if you have something in sine, and it doesn't matter to what power, but your other one, the cosine, is to degree 1. Or it could be the other way if you have cosine to the 10 times sine to the 1. As long as you have that, the other one of the cosine and sine, as long as the other one is to a power 1, then we can do nice easy substitution. Let's say let U equal, in this case we're going to want sine x, and therefore you differentiate that, du is equal to cos x dx. And that really is where this is going to fall out, is the fact that the derivative of sine is cos, and so we have that just degree of 1 of cosine, and so therefore this ends up being equal to the integral of u to the 10 and then times du. We integrate that nice and easily, add 1 to the exponent, divide by that. We have to remember that this is plus c, and then when we substitute this back in, let's call this 1/11 sine to the 11 x plus c. So if this question would have been cosine to, I don't know, to the 7x sine x dx, as long as it's in this kind of format, that the derivative of cos, it's just sine to the 1. And so as long as it's in that kind of format, it's going to be this relatively simple, straightforward type 1. When you get into university level integration, there are more scenarios than just these that you're going to look at, but for now, we're just going to look at these ones. Type 2. So if cos is, if you're trying to integrate cosine, or if you're trying to integrate sine, where your exponent on that is odd. So in these cases, you either have the integration of in this case, we've got cos cubed, or if we had just sine cubed, what we're going to do is we're going to use our trig identities. And the simplest one that we saw, the first one that we saw last semester, was cos squared plus sine squared is equal to 1. And we're going to break this cos cubed apart and use that. So remember that cos squared plus sine squared equals 1 gave rise to, therefore, cos squared x is equal to 1 minus sine squared x, just by subtracting. And so what we're going to need to do with our integral is we're going to break cos cubed apart into cos squared times cosine x, cos squared x times cosine x dx. And maybe you can see where we're going with this is if cos squared is the same as 1 minus sine squared, let's do that substitution. And then this ends up just being equal to the integral. If we distribute that across 2 terms, then this ends up being the integral of cos x. I'm going to break it apart into 2 integrals as well, minus cos x sine squared x dx. This first one is just sine x. This next one is now we're going to do a u substitution again. So we're going to say that u equal sine x. So therefore du is equal to cos x dx. And when we do that, then this ends up being the integral of u squared du. Du is the cos x times the sine x there. And so we're almost there. This ends up being equal to sine x over 3 plus c. And then we do our substitution back here. And we end up with sine x minus sine cubed x over 3. If we have a double angle in here, there are some, later on, we're going to use maybe some of our double angle identities. For now, we can just leave it be as this double angle. It is going to affect what we would do with chain rule in here. But let's still break it apart into even and then an odd one. And so what I mean by that, let's break this apart into sine 4 2x sine 2x dx. We have a power of 5. Let's break that into 4 and 1. This ends up being equal to the integral of sine squared x squared times 2x dx. We're now going to change that inner sine squared into 1 minus cos squared 2x. This is still all being squared. Sine 2x dx. And now we're going to square that out. We're going to distribute two binomials. And this ends up being equal to, in brackets, 1 minus 2 cos. Still remains 2x is inside our cosine. And then we have plus cos to the 4. All of this is being multiplied still by 2x dx. And we're going to distribute and get sine into this bracket. So this ends up being the integral of sine 2x minus cos squared. Oh, sorry, I missed a cos squared on this here. Better change that. So this is minus 2 cos squared. So what do we have here? We have minus 2 cos squared 2x sine 2x. And then we have plus cos to the 4 2x sine 2x. This all times dx. Let's put brackets around that, so that's proper. Let's break this apart into separate integrals before I do a u substitution, and let's call this integral sine 2x minus the integral. I'm just going to shuffle this around a little bit. I'm going to call this cos squared 2x times 2 sine 2x. Just going to move that 2 over here. You'll see why in a moment. Dx. And then this is plus the integral of cos 4 2x. 4 2x, sine 2x, dx. We're going to let u equal cos 2x, and the derivative of that, du. The derivative of cos is negative sine, but we have 2x, so we're going to have to chain rule that. So this is du is equal to negative 2 sine 2x dx. So let's go ahead and integrate that now. So therefore, this is going to be equal to sine 2x. We can integrate that one directly. This ends up being negative 1/2 cos 2x. This next one, this ends up being, this is u squared down here, is your cos squared 2x. And so I integrate that, and you get minus u cubed. We integrate that, we have to divide it by 3. But the 2 sine x, negative 2 sine 2x dx, most of it's right there, except for the fact that it's negative. So we're going to change this to plus u cubed over 3. And then we have u to the 4 is this term. So this ends up being u to the 5. I'm going to divide it by 5. But notice that with our du is equal to negative 2 sine 2x dx, missing from there is that negative 2. So again, we're going to change this to subtract to account for that negative. But how do we account for the fact that there's no 2 in front of that? Well, I mean, we could call this 2 times this, and then also multiply it by 1/2. And so really this ends up being u to the 5 over 5, but also dividing by 2. C on the end ends up being equal to negative 1/2 2x plus 1/3 cubed 2x minus 1/10 cos to the 5 2x plus c. Lots going on in that question. Lots and lots and lots. Type 3. So if we have a derivative that's just in cos or just in sine, and where n is even, so using our trig identities from last semester, from the double angle identities, one of the double angle identities for cosine was cos squared minus sine squared. And then if we couple that with this Pythagorean identity of cos squared is equal to 1 minus sine squared, then our cos 2x ends up being 1 minus sine squared minus sine squared x. So just substituting that in for cos, which ends up being 1 minus 2 sine squared x. And then if I shuffle that around and solve it for sine squared, we end up with a new identity for us, 1 minus cos 2x over 2. We can do a similar thing with sine squared, and we're going to let this sine squared equal 1 minus cos squared x. And so therefore this identity ends up being cos squared x minus 1 minus cos squared x. Ends up being 2 cos squared x minus 1. And then shuffling that around and solving it for cos squared, we get cos squared x is equal to cos 2x plus 1 all over 2. And we're going to use these new identities here. The idea is last semester when we were working with this in 30-1, we were solving it for x, and we were wanting to get rid of 2x as your argument for cos or for sine. And so we were wanting to use our double angle identities to get rid of that. In this case, we don't really have a problem in integrating cos 2x as long as it looks a little simpler. Cos 2x is going to be easier to deal with. So in this question number 4, if we have sine squared x. So type 3, remember if you just have sine or cos and your power is even, let's change this around and we're going to call that's going to be equal to 1/2, sorry, the integral of 1/2, it doesn't matter, 1 minus cos 2x dx. We can bring that 1/2 outside of the integration. And now we're just integrating 1 minus cos 2x. First term is just x, and this ends up being minus the integral of cos 2x dx. This ends up being 1/2 times x. We now integrate that cos 2x, ends up being sine 2x. But remember, we also have to divide that by 2. And we now have plus c. We're going to leave that plus c out there, which leaves us with 1/2 x minus 1/4 c. Integral of cos squared 3x dx. So we're going to use this identity, that cos squared that we did on the previous page. Cos squared x is equal to cos 2x plus 1 over 2. And then when we use that in this one, the 3x ends up doubling. So just like the x ends up being twice as much more as 2x, then this ends up being equal to 1/2 cos 6x plus 1 dx. This ends up being equal to 1/2. The integral of cos is sine, so this is sine 6x over 6 plus 1. So this ends up being plus x when we integrate that. We have plus c out here, and both of those are being multiplied by 1/2, so this ends up being sine 6x 12 2 plus c. Number 6, the integral of cos to the 4x dx is equal to the integral cos squared x squared dx. And then this ends up being equal to 1/2, the integral of 1/2 cos 2x plus 1. This is all being squared still, dx. So just doing our same identity substitution that we did in the previous question. This ends up being equal to, let's break that 1/2, and we're going to square 1/2 into being 1/4. We're going to bring that outside of the integral. We're going to square that binomial of cos 2x plus 1. Ends up being cos squared 2x plus 2 x plus 1. Just multiplying out that binomial. This still needs dx. And then we're going to do this double angle again with that first one. So this ends up being equal to 1/4 times the integral of 1/2. We're going to call this cos 4x plus 1, because we double that angle. And then we have that. Let's do our integral of cos 2x. Makes this, there's 1/4 that was sitting up front. And this ends up being the integral of sine 2x, sorry. We're dividing it by 2, but we're also multiplying by that factor of 2. And then the plus 1, which is just 1/4 x. Let's see. So we've found the integral of some of those terms. This term we haven't done yet, so we do need a dx in there still. But this is now 1/8 times the integral of cos 4x, which is sine 4x, 4. The integral of the plus 1 over here is going to be plus 1/8 times x, because we have this factor of 1/2 also. So 1/8 of sine 4x over 4 plus 1/8x plus 1/4 sine 2x, 1/4x plus c, and it just needs a tiny bit more tidying up. This is equal to sine 4x over 32 sine 2x over 4. 1/8 plus 1/4 of x is plus 3/8 x. C. Number 7. So question 7 just kind of ends up being a more complicated looking type 1. Even though we have sine cubed and we have cos squared here, we're going to try to separate, get a single factor of either cos or sine, and then we're going to use our trig identities to change the other one so they're both in either cos or sine. So in this case, we have the fact that this is sine cubed x. Let's call that the integral of sine squared x times cos squared x times sine x dx. So just breaking apart that sine cubed, the sine squared becomes 1 minus cos squared x. That's multiplied by cos squared x sine x dx. Distributing that across that binomial is the integral of cos squared x sine x dx. And then I'm going to subtract the integral of cos 4x cosine x dx. Just breaking that apart now into two integrals. So we're going to do a u substitution now. And we're going to actually do it twice. And we're going to let you can probably guess, u should equal cos x du is equal to negative sine x dx. Let's do this first with the first integral. And so now this is equal to integral of negative u squared du. Minus the integral of u to the 4 times du. But our sign changes because this is du is negative sine x, so let's change this to plus. So this ends up being equal to negative u cubed over 3 plus u to the 5 over 5. We're going to integrate each of those. And then plus c. Negative cos cubed x over 3 plus cos 5 x over 5 plus c. Which brings us to our last type. And so we have what we're going to call type 4. And we have something that doesn't even have trigonometry in the question when you're asked to integrate something that looks like what we have in number 8. So we don't even have any trig going on in there. But what we know about this is square root of a squared minus x squared looks Pythagorean. And in fact, we are going to do a trig substitution. So let's draw our triangle out because this is going to be relevant for us. What we're going to substitute is we're going to substitute x is equal to a sine theta. Is going to be one of them. Also, we know that cos squared is equal to 1 minus sine squared. That's going to be relevant here. We do need this domain of from negative pi halves to pi halves. This is so the inverse is still going to exist. And so here we go. We're going to set up theta in our triangle. This theta is going to be one of our angles. And in this question, it's saying integral of 1 over x squared times square root of 1 minus x squared. So in this case, a is just 1. And so if we let x equal, it's going to be a sine theta, but in this case, so therefore it's 1 sine theta, dx ends up being equal to cos x d theta. And when we do our substitution, this x squared has become sine squared theta. And the part underneath the square root is 1 minus sine squared theta. Dx has been replaced with cos theta d theta. We're going to come back to our triangle in a minute here. In our next step, is equal to the integral. Here we have sine squared theta. Downstairs, the square root cos squared theta is what 1 minus sine squared theta is equal to. We have a factor of cos theta came from the multiplying by d theta. So this ends up being the integral of cosecant squared theta d theta. Cos theta in the numerator and the square root of the cos squared in the denominator divide away, and we're left with 1 over sine squared, which is cosecant squared. Now back to our triangle for a second here. If we've made this substitution, if x is equal to 1 sine theta, then from theta, opposite over hypotenuse, this is x over 1. which makes this square root of 1 minus x squared. Drawing a diagram like that's going to be kind of helpful for us when we get to the end here. The integral of cosecant squared, so remember your derivative of cotangent is negative cosecant squared, so this ends up being equal to negative cotangent theta. C. But we need this triangle to figure out what cotangent therefore is, and cotangent is adjacent over opposite, so we end up with square root of 1 minus x squared over x. It's negative cotangent, so negative of that, and plus c. So very different looking. It's unexpectedly trigonometric. And let's do one more. In this case, our a is, we have square root of 4 minus x squared, so therefore a is 2. So we're going to let x be 2 sine theta. Therefore, our dx ends up being 2 cos theta d theta. What we have for our integral is the integral of 1 over 4 sine squared theta. When I square x, it's 2 sine theta times 2 sine theta, so that's 4 sine squared theta, times the square root of 4 minus 4 sine squared theta. Dx is 2 cos theta d theta. So this is equal to, let's move that numerator in, 2 cos theta d theta. I'll leave the d theta out here. And what do we have going on in here? We have 4 sine squared theta. If I common factor a 4 out from this 4 minus 4 sine squared theta as the radicand, and then I square root that, that comes out as a 2 times square root of 1 minus sine squared. So we're factoring 4 out, but it's under the radical. Square root 4 is 2 when it comes out. This simplifies out a bit, and this now ends up being integral. 2's divide away. We still have cos theta upstairs, but that's going to be gone pretty soon. Cos theta over 4 sine squared theta times the square root of cos squared theta d theta. And we're almost done because the square root of cos squared is just cos. That divides away. And so this is equal to 1 over 4 cosecant squared theta d theta, just kind of like in the last one. So this is equal to negative 1/4 cotangent theta plus c. Let's maybe draw this triangle with theta here just to get our head around what we had. We had sine was, so x was equal to 2 sine theta. We had up above, so x is equal to 2 sine theta, so therefore sine theta is equal to x over 2, which means this is x, which means this is 2, which means by Pythagorean theorem, this is 4 minus x squared, the square root of that. Therefore, cotangent is equal to negative square root 4 minus x squared all over 4x Let's see. And if you have any questions, please ask. Thank you.